Welcome back to compiler construction. In the previous lecture, we took a closer look at how scanning works in a compiler, and now we'll continue with parsing, so the next step in our compiler toolchain that enables us to understand some input source code. So first, we're going to look at the compiler structure again, and especially how scanners and parsers interact in a compiler. And then we'll take a look at how to specify the rules that describe how a parser works. So we start with a very simple language or set of languages we can describe, so-called context-free languages. Then we take a look at grammars describing them and the problems of ambiguity of these grammars. Then we take a look at one standard form of describing grammars called the Backus-Naur form or BNF grammars. And finally, we'll take a quick look at language classes and the Chomsky hierarchy. So you've seen this diagram in one of the first lectures of compiler construction already. So this shows that we start off with some source code as a text file, which is just treated as a character stream by our scanner, by our lexical analysis. And in the previous lecture, we've seen that this lexical analysis returns a sequence of tokens. So it splits our source code into lexical units. It recognizes tokens using regular expressions or automata, as we've seen and constructed before. And we know a token is a character sequence relevant to the grammar of our source language. So we have this character stream here consisting of the characters x equals y, a plus character, a digit 4 and a digit 2. And now our scanner performs the tasks of splitting this up into some sequence of tokens that are meaningful. So let's say we want to write a language that allows us to automate calculations. So we have variables that can be indicated by a character name x or y. We have numbers that are sequences of digits, so integer numbers. We have some operators like a plus sign, and we have an assignment operator that assigns a new value to an existing or a new variable here. So our scanner splits this up, so it first recognizes using a rule that says, oh yeah, a single character maybe. This is an identifier, so a variable name, and the value of that identifier is the name of the variable, that's x. The next character in sequence is the equals character, so this is an operator. The following character is an ASCII letter y, so this is another identifier. Then we have a plus, which is another operator. And finally, our scanner finds that we have a 2-digit sequence 42. So for the scanner, depending on which rules we give it, this is a number, and the number has the value 42. So this is the token sequence our scanner actually generates, and this is what our parser can then build upon to try to reconstruct the structure of the input. So this is passed to our syntax analysis or parser. So syntax analysis takes the token sequence and reconstructs some structure like that one here, a so-called syntax tree. So from our simple input string, we derive that we have some sort of hierarchy, which means we have the equals operator in assignment. So we know to the left of the equals operator is always a variable name, and to the right there may be some expression, and this expression consists of another operator. And this operator then connects our variable y with our number 42. So our syntax analysis or parsing needs a grammar of the source language. And this grammar is used to describe the language's structure. So we see a simple grammar down here. So we'll go into details on this later. So we have an expression at the top. And from this expression, we can derive a term and then optionally a plus or minus sign and another term. A term can consist of a factor, a multiplication or division sign, and another factor optionally. And a factor can be either an expression in brackets or an identifier or a number. So the task of the syntax analysis is first to decide if this input token sequence makes sense in the context of our language. So if this can be derived from the grammar, so if this is a valid program in terms of our grammar. If not, it will print an error, so you can try to fix your program. And if it finds that actually our input program is correct, then it generates such a syntax tree out of the input. So we have some structure that's recovered from our text input stream. So in the previous diagram, it looked like first we run through the scanner. The scanner just generates a token sequence for all of the tokens in our program, and then our parser starts to work. Well, you can do it like this, but this makes programming a bit more complex than it's needed. So in real-world compilers, the scanner and the parser actually interact. So what happens is that actually our parser starts, and needs the first token because it needs to figure out where do we start with. So the first thing our parser does, it requests a token from the scanner. The scanner reads a bit of the input sequence here and returns the token plus the value of the token, and then the syntax analysis can figure out, does this actually fit our grammar? And if yes, it can add the element to the syntax tree. So the parser requests next tokens from the scanner, and the scanner then reads the next bit of our source code that hasn't been read before and returns the next token that was requested. So we have a regular expression set here describing our tokens. So let's say we start with a language we've seen before. So we have some tokens here. One token is a token number, which consists of sequences of digits, which are at least 1 digit long. Then we have another token, which is an identifier, just ID. And this consists of a uppercase or lowercase character at the start, and then an arbitrary long sequence of uppercase, lowercase characters or digits, and this can also be 0, so single character variable names are perfectly fine. But a variable name may never start with a digit, because a digit, if it occurs, can only occur as a second or subsequent character. And then we have operators. One operator here is the equals sign, and another operator is the plus sign. We've seen this for Lex syntax. Plus has this special meaning of being the closure of at least one repetition of an element. So if we want a literal plus to be detected, we have to escape it by writing a backslash character in front of it. So our syntax analysis starts and requests the first token. So let's say we have the token sequence from the previous slide. So it gets an ID of X, and with an ID of X, it has to continue. So essentially what our scanner does, or parser does, it goes through the syntax, starts somewhere, tries to fit it in, like it finds a plus character somewhere here, which is here, and then it constructs this syntax tree piece by piece, and when it ran out of tokens to construct its syntax tree, it requests the next one, like the equals sign, like the variables, the plus, and the 42. And we'll take a look now at how this works in detail. So, as we've seen, parsing is the second stage of the compiler's front end, and this works with parts of the program, so our tokens as transformed by the scanner, and it sees a stream of words, and we've seen each of these words or tokens is annotated with a syntactic category. So we see there's a word which consists of the digit sequence 4 and 2, and we've already seen in our Lex introduction this is stored in YY text, and this 42 is annotated by the token category, so we say this is the number. So whenever our parser requests a token from the scanner, it gets such a tuple back. So we have a token that's a number, and this number has the value digits 4, digits 2. So our parser tries to derive a syntactic structure for the program we feed it. So as we've seen, it tries to fit the words into the grammatical model of the source programming language. And as I already mentioned before, there are two possible outcomes of this. Either you manage to write a program without any errors, so this means your input is valid. So our parser can build a concrete model of the program, so it can reconstruct the structure because your input program had a valid structure. And this can be used by later phases of compilation. Or if you made some mistake, your input is not a valid program, so your parser should be able to report a program and a diagnosis, and maybe even propose what you can do to fix the problem. So let's define parsing a bit more formally. The task of the parser is to determine if the program being compiled is a valid sequence in the syntactic model of the programming language. And if we want to describe this in a bit more formal way, let's say the syntactic model we are talking about is expressed as a so-called formal grammar G, and some string of words S is in a language defined by G, so a grammar defines a language. And if some string of words can be generated by this grammar G, so it is in the language defined by G, we simply say that grammar G derives a string S. And for a string or stream of words, S and a grammar G, the parser then tries to build a constructive proof that S can be derived in G. Now that sounds very horrible and mathematics heavy, but it's not that bad. So this is essentially, this proof is called parsing. And a proof simply shows the absence of any mistakes in the input, and then by doing it constructively, it constructs an abstract syntax tree, and when it ran out of tokens to read and it has a valid syntax tree, then this is our constructive proof that the input program could actually be derived by applying this grammar. And of course, it's not as bad as it sounds, because by writing a compiler, of course, we let the computer do most of the work. So how do we specify the language syntax? So we need some sort of formal mechanism, because a computer needs to be able to understand it. And this formal mechanism is used to specify the syntax of our source language. So it is the grammar of our source language. And then we need a systematic way to determine, if some string or some character sequence we input or some token sequence is a member of this formally specified language. And this is parsing. So let's make our life a bit easier for now. First, we want to restrict the form of the source language to a set of languages we call context-free languages. And for context-free languages, typical parsers can very efficiently answer the question if some given input is actually, yes, a valid word or sequence in this language. So if a grammar can derive this given input, or if there is some mistake in it. And there are a large number of different parsing algorithms. We'll take a look at specifically two different approaches. The first one is top-down parsing. And in top-down parsing, there are two very common types of parsers. The first one is a parser that's called recursive descent, which more or less orients your program structure of your parser according to the language you're trying to parse. And another one is LL1 parsers, and you can do bottom-up parsing. And one of the typical representatives of bottom-up parsers is an LR1 parser. You don't need to understand right now what LL and LR means. We'll go into detail on this a bit later in this lecture. So let's look at these two classes of parsing first. So top-down parsing. As we've seen, recursive descent and LL1 parsers are members of the class top-down parsing. And top-down parsers try to match the input stream against the productions of the grammar by trying to predict the next word at each point going through our token stream. So essentially, it goes through our grammar and it tries to figure out what can be the next symbols or tokens that can appear. And if one of these tokens can appear, it can proceed. And if another token appears that's not predicted by the grammar, then it flags an error. So for a limited class of grammars, such a prediction is both accurate and efficient. Bottom-up parsers try to work the other way around. So a bottom-up parser works from a low-level detail. So it first looks at the actual input sequence of words, and then it tries to accumulate enough context, so following tokens and so on, until it knows that there is a derivation. So until it finds a matching rule in our grammar that can actually tell us, okay, this token sequence matches this rule, so it's part of that one. And then it goes bottom up and constructs our syntax tree from the leaves of our tree back to the root of our tree. Again, also for bottom-up parsing, there exists a restricted class of grammars for which we can generate efficient bottom-up parsers. Now this sounds like this would be very restrictive, but in practice, these restricted sets of grammars are large enough to encompass most features of interest in computer programming languages. If we wanted to parse something else like natural languages, so just a sentence you type, this is much more complex because natural human languages can have much more variation or ambiguities and so on than we allow for computer languages, which are very strict and formal. So how do we express syntax? We already know one way to express syntax, and this is by using regular expressions. And the question is, can we simply use regular expressions also to express such a grammar? Well, obviously not, because then we would be done already. So we need to ask us, why are regular expressions not suitable for describing the syntax of a language? To take a look at this, we'll first examine this example here. So let's try to recognize algebraic expressions over variables and the four operators plus, minus, times, and divided. So let's try to write regular expressions for this. So a variable is, well, character A to Z. Let's just restrict ourselves to lowercase characters here. And then an arbitrary repetition of ASCII characters or digits. So note we write the character sequence here no longer as A-Z, but we use A dot 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 Z. This has exactly the same meaning in regular expressions for our course here. So what we can have here now, we want to express arithmetic expressions over our variables here. So we don't consider numbers here, we're just using variables. So an expression can be a variable name here, and then an arbitrary long repetition of what's inside of our brackets. And inside of our brackets is one of the operator symbols here and another variable name. So this regular expression matches, for example, A plus B times C, or D divided by day times do. But there is one problem. So there is no way to express operator precedence. So the question we need to ask is, which operator needs to be executed first? So should a plus operator or multiplication operator be executed first in an expression A plus B times C? And you know the standard rule from school, your standard algebra rules that says the multiplication and division symbols or operations have precedence over addition and subtraction. So if you just try to evaluate such an expression from left to right, you'd add A plus B, and then you'd multiply the sum of A plus B to C, which gives us an arithmetically incorrect result. So we need some way to express this operator precedence, so to express a hierarchy or an order of evaluations in our expressions here to get the syntax right. So the problem is there is no way in regular expressions to express this operator precedence. So what we can do or can try to do in a regular expression to enforce evaluation order, we can use parentheses. So essentially everything that's in parentheses is evaluated first, and then we look at everything outside of those. So this gives us a little problem in notation, because we've seen we already use parentheses as a meta element here in a regular expression to denote a grouping of symbols. So when we want to use a literal parentheses character, we have to include it in double quotes as shown here. So double quote, opening parentheses, and another double quote. This is a bit tedious, but that's the way we need to do it, because our computer needs to be able to figure it out. So adding parentheses in regular expressions is quite tricky. We can try to do it this way. Let's say an expression starts with an opening bracket. The one here we showed in red. So we need the option for an initial opening bracket. So we start, put our expression as we had it in here, and then we add something to the beginning, which is either an opening bracket or epsilon, so an empty character or nothing at all. And so if we have an opening bracket, we need the option for a final closing bracket here. So that's this one here. So this is either a final closing bracket or an epsilon. So this regular expression can produce an expression that's enclosed in parentheses, but we specify that the parentheses are only at the beginning and at the end of our expression. So this regular expression is unable to generate an expression that has internal parentheses to denote precedence. So that's not that useful for us. So what else can we do? Now we can try to add internal instances of our opening bracket, and we figure out that all opening brackets must occur before a variable. And similarly, the internal instances of the closing brackets all occur after a variable. So let's extend our regular expression by shuffling it around a bit. So let's try to move the closing parentheses now inside of our final clean operator here, so our final repetition operator. Now amazingly, this works for matching some bracketed expressions here. So this regular expression matches both a plus b times c. So it works by just ignoring the bracket because it can take an epsilon here, then it has an a here, and then it can match a plus here, then it can match another variable here, then I can ignore that bracket here, and then it can go from the start again and match the rest of our expression here. Okay, so this can also match opening bracket a plus b closing bracket times c, because it can read these bracket characters inside of the repetition that's available here. So essentially, this is also able to express bracketed expressions. And the nice thing is, which sounds really good, it will match any correctly parenthesized expression over variables and or for operators in the regular expression. But there's one big problem with this. This expression also matches expressions which are syntactically incorrect, so which have a non-matching number of brackets or a bracket in an incorrect place. So for example, we can also match a plus opening bracket b times c, no closing bracket, or a plus b closing bracket times c closing bracket, because we have a bracket or the epsilon to choose at the beginning and the end. So essentially, these strings would match the case where we match one of those with a bracket and the other one with an epsilon. And it's impossible to write a standard regular expression to match all the expressions that have balanced parentheses. So to have this balancing of parentheses here, you need to be able to count. So how many opening parentheses do you have? And then you need to match the same number of closing parentheses, and you need to ensure they're in the right positions. A DFA or a regular expression cannot do this because it's restricted in its compute capabilities. So a DFA cannot count. So we need something better. For this something better, we first try to derive a notation that works better or is more powerful than our regular expression. And this is a context-free grammar. Of course, we still want to have expressions that lead to efficient recognizers, so it should be compact, it should be easy to work on for a computer. This traditional solution of using a context-free grammar, or just CFG, uses two terms. The first one is just a grammar, as we've seen before, the set of rules that describe how to form sentences, and then all the sentences, all of them, that can be derived from G. These are called the language L of G, defined by G. So all the sentences we can derive from this grammar we've given. So let's start with a very simple example of a grammar we call SN for sheep noise. So this thing just generates sheep noise. So sheep don't generate, well, I never had sheep, but I can imagine sheep don't generate a very varied language, but can only say, for the sake of example here, ba. So what do we have here? We have some rules here, so some derivations, and we say, let's just take it by intuition. A sheep noise is something that's a ba and another sheep noise after it, so it can be ba ba or ba ba ba, or it can be a single ba. So each line in this grammar describes a rule, or we also call it a production of this grammar. So when we want to generate sheep noises, we can either use the first production of this grammar or the second production of this grammar. So how can we now express something we cannot express using the regular expressions? Let's see how this works. So the first rule we have here So sheep noise, that starts with sheep noise, can be read like sheep noise, and then our arrow is read as can derive a word, and this word is ba, the first one here, and then it follows by more sheep noise. So what you see here, we are writing the things in our grammar in two different fonts. So we have italics fonts here for sheep noise, and we have bold characters for ba. And these are different classes of symbols in our grammar. So sheep noise is a syntactic variable that represents the set of strings that can be derived from the grammar. And this is like a variable in some respects. So we call this syntactic variables non-terminal symbols, or simply NT. So non-terminal means our production of our grammar, our analysis of the grammar can never stop there. So we can never say, oh yeah, we have a sheep noise and we're finished. So we need to derive something from sheep noise and continue doing this until we have no non-terminal symbols in our grammar again. So each word in the language is defined by the grammar, then is a terminal symbol. So this is the bold letters here, and these terminal symbols cannot be derived any further, so they correspond to some character sequence in our input text, like the character sequence BAA for our bar here. So the second rule now reads, well, that was the first one. The second rule now reads, the sheep noise can also be derived as the string bar and nothing after it. So you cannot read this as sheep noise can derive bar sheep noise, or this is the pipe character here, it can simply derive the terminal symbol bar. So this pipe notation is just a shorthand. So this avoids writing two separate rules. Sheep noise derives bar sheep noise, and sheep noise derives bar. So that makes it a bit easier to group and to read, and it saves you a bit of typing. But you could also use the second form if you liked. So can we now figure out which sentences can be derived from a given grammar? So what are valid sentences in our language L that is generated by our grammar G? So first, we need to figure out what is our goal or start symbol of our grammar. So we need to start somewhere in our grammar. Our grammar is a hierarchy. And the first symbol we start with, so the first rule of the grammar we actually read to be able to derive a syntax tree afterwards, this needs to be specified. So this gold symbol represents the set of all strings in our language. And from this gold string, we now have to be able to derive all of the words that are valid in our language. Accordingly, it cannot be one of the words in the language, but it's just an element of our grammar. So it must be one of the non-terminal symbols that we introduced to add structure and abstraction. So if we look at our sheep noise grammar here, well, we only have one non-terminal symbol here, written in italics. This is sheep noise, so obviously sheep noise must be our start symbol here. So we start here, and now see we added line numbers to our grammar. These are not part of the grammar. They're just make it a bit easier to talk about what's going on here. So when we try to derive a sentence, we start with a prototype string that just contains the start symbol. So we start with a sequence of elements of our grammar, and the first element we start with is just our start non-terminal symbol sheep noise. And then we pick one of the non-terminal symbols in the prototype string, look which rules apply to this non-terminal symbol, so what can be derived from this non-terminal symbol, and then we replace the left side of this production with the right side. So essentially we can say, okay, we start with sheep noise, and this is the only non-terminal symbol, so we now need to take a look which sequences can be derived from sheep noise, so that can be either the first one here, or the second one here, and then we can replace sheep noise by something on the right hand side. So we change our prototype string that contains sheep noise, for example, to contain bar sheep noise. And then we need to continue this until the prototype string contains no more non-terminals. So then finally the string only consists of words, so of essentially tokens of our input language, so terminal symbols, and in the terms of our grammar. This means the string is a sentence in the language, and if we've derived something from this, we know okay, this is a valid string, so a valid input for our grammar. So every version of the prototype string that can be derived, we just call it a sentential form. So some sort of a prototype for a valid sentence in a language. So let's take a look at an example. Again, we use our sheep noise grammar here, and we want to start to derive words from our grammar. So we start with our only non-terminal symbol, our start symbol sheep noise here, and then we can choose which of the two rules, 1 or 2, to apply. So let's say in our first example, we are just applying rule 2 immediately. So we start with a sentential form sheep noise, and then when we apply this rule 2, we know that we replace sheep noise in our sentential form by whatever is the right side of our production. So the right side of our production in rule 2 is simply the non-terminal symbol bar. So we rewrite with rule 2, so we derive bar, and then in this new sentential form, which we just replaced, we figure out, oh, there's no other non-terminal symbol, so we're finished because we cannot go any further. There's nothing more to derive. There's only terminal symbols in the sentential form. So we derived the first valid word, part of our language, generated by G, which is just bar. So bar would be a valid expression in our language. Let's look at a slightly more complicated example. So again, we start at sheep noise, and then we use the first rule first, derive bar sheep noise. So we replace in our sentential form sheep noise by the right-hand side here, bar sheep noise. So we have another non-terminal symbol inside of our sentential form. So we have to go through the grammar again to choose another production that's valid for sheep noise. And let's say now we choose to use the second production here. So we replace this non-terminal symbol in our sentential form by this terminal symbol bar. So now we have derived another valid word of a language, which is bar, bar. So when we rewrite rule with rule 1 first, we need to do another recursion through our grammar to finally get to a sequence which contains no more non-terminal symbols. So we see applying rule number 1 lengthens our string because we add a non-terminal symbol, whereas applying rule number 2 shortens our string because it eliminates the non-terminal symbol sheep noise. We've also seen the string can never contain more than one instance of sheep noise because we can only generate one instance of sheep noise using rule 1, and this has to be replaced again by a recursive application of that rule or the other one. So all valid strings are derived by at least 0 applications of rule 1. And finally, we need to eventually apply rule 2 because we need to have a string at the end, a sentential form that only contains terminal symbols and no more non-terminal symbols. So applying rule 1 k times, followed by a final application of rule 2, would generate a string that contains k plus 1 by the final bar repetitions of bar. So this is a very simple example. Of course, real languages are a bit more complex. Let's look at a more useful example here. Again, we want to parse expressions. So we need to describe sorts of expressions. And we have seen the problem before that expressions should have some sort of representing or some way of representing operator precedence. So what we want now is we want to include brackets as well as names and operators. So we start with a non-terminal symbol expression, and from expression we can derive something that is just another expression now enclosed in an opening and closing bracket. So what you see here is we must always match an opening bracket to a closing bracket because we only derive the whole form on the right-hand side and not just part of it optionally. If we don't want brackets, an expression can consist of yet another expression, so this is again a recursive definition, followed by an operator, followed by a name, or an expression can simply be a name, because a single variable is a valid expression like Q or something. And then we have another rule just giving us the operators. So the operator always resolves to terminal symbols, and these are our 4 arithmetic operators we want to use in our expressions here. So let's look at some sentential forms, some stuff we can derive here. So one thing we see, we have name here. So name is just a token class we use for a parser, so that can be an identifier for a variable name. So this is not necessarily matching a specific variable with a specific name, but a class of variables, for example. So let's start with our start symbol. So here we have the convention that our first non-terminal symbol is our start symbol. So we start with expression, and then we use rule 2 and derive the sentential form expression operator name. So name is a terminal symbol, and then we have to go through our grammar recursively for both new introduced non-terminal symbols, expression and operator. So then let's first look at operator, and let's choose rule 6, which resolves to a multiplication symbol. So we replace the right-hand side in our sentential form by expression. So we still have one non-terminal symbol. We do it one at a time, times name. Okay, so we still need to resolve expression here. So we can choose rule 1 now. So this adds brackets around it. So rule 1 replaces the expression on the left-hand side by an opening bracket, another non-terminal expression, a closing bracket, and the rest as we've seen before. And then we need to resolve expression again. Now we can choose rule 2 up here. So we can say expression is replaced by expression, yet another operator, and a name. We leave the rest unchanged, of course. Then again, we replace the operator here. Now we choose rule 4. So we replace the operator by a plus sign. And the rest stays the same. And now finally, we can choose rule number 3, which replaces our remaining non-terminal expression here in this sentential form by yet another name. And so we can have a valid sentence that has the form opening bracket, a name, the operator symbol plus, another name, closing bracket, times yet another name. And as we've seen, name is just a token class, so an identifier for a variable, for example. So this would be the so-called rightmost derivation, because we start replacing things from the right to the left of, for example, this expression here, opening bracket a plus b. So you see these variable names are just instances of our token class name. So opening bracket a plus b, closing bracket times c. And from this we can derive our first parse tree here. So this parse tree actually represents the way we followed through our rules and then just splits up the components. So whenever we ended up at a terminal symbol, we replace this by just a terminal symbol, which is a leaf of the tree. And whenever we resolve a symbol to another non-terminal symbol here, then we have another internal node in our tree. So we can say our expression, we start resolving from the right. At the right has a name. This name now is a type of a token and has a value c, because it's the name of the variable here. The next thing we resolve from the right is, okay, we resolve expression to an operator. This is still a non-terminal symbol. This is a multiplication symbol. And on the left-hand side, we resolve expression to another expression. Add the brackets around here. And then we have another NT expression in here, which we can resolve again to expression operator name of b. We start on the right-hand side again. So we get our next token b, which is another name. We go one step to the left, derive an operator non-terminal symbol, which is a plus here. And finally, we end up on the left here, which is yet another expression. And then we can finally use this terminating rule 3 here, which resolves the symbol to name of a. So what you have here at the leaves of your parse tree is only non-terminal symbols, and the internal nodes of your parse tree is only non-terminal symbols. All right. So this simple context-free grammar for expressions is great because it cannot generate a sentence with unbalanced or improperly nested parentheses, because we always add an opening and closing set of parentheses around an expression, and as we have to go through all of this recursively, we can ensure that the expression inside of our brackets is also valid, even if we include more brackets, because we're going down the chain and up again to continue all of our parsing here. So only rule 1 can generate an open parentheses, and this automatically after going through expression and whatever here, also generates a closing parentheses. So it's unable to generate strings like this one here with just one opening bracket, or this one here with two closing but no opening bracket. A parser, which we built from that grammar, will not accept such strings, so it will print some error message that says, okay, something's wrong with your input. So you see, context-free grammars have more power than regular expressions because they allow to, due to recursion that's now applicable, which regular expressions don't support, so they allow to specify constructs that regular expressions are unable to express. And from this, we can easily derive from the derivation steps we took throughout our grammar, this parse tree, which we can construct on the fly when reading our token stream. So we've seen one order of derivations, the rightmost order, and the rightmost order tells our parser to rewrite the rightmost non-terminal symbol first at each step. So we've seen this one here. We started with the rightmost symbol, like replacing name here, then replacing the operator, and then finally replacing the left symbol expression by something else. And then we start again with the rightmost, and so on and so forth. You can also do it the other way around. So you can try to rewrite the leftmost non-terminal at each step. So we take another walk through our grammar here. So we start with expression resolving to expression operator name, because expression, well, it doesn't matter if you do it left or rightmost, it's only one. And then you start replacing on the left-hand side. So you start replacing the expression here on the left with two brackets around expression. Then you start again with replacing that expression here. So you keep the right-hand side with a non-terminal symbol here, replace this expression with expression operator name. Then you find the next symbol on the left-hand side, which is expression. You replace it by name. Then you have the next non-terminal symbol replaced by a plus. And finally, when you end up replacing all the non-terminal symbols on the left here with terminal symbols, you can now continue to the next unresolved non-terminal symbol, which is the operator. And then we end up replacing that one by a multiplication sign. Now, what's interesting is, no matter which way you choose to walk through your grammar, so if you do the rightmost derivation first or the leftmost one, your parse tree is identical for both, because that's obviously what you want. You want a unique parse tree no matter which way you apply your grammar rules, because that is, except for the starting rule, not set in stone. So you can choose the order, whichever order you like. So for the compiler, it's very important that each language in the language, each sentence in the language that we define by a constant context-free grammar has a unique derivation. It can be unique rightmost, or as we've seen, a unique leftmost derivation, which results in the same parse tree. If we have a grammar that allows multiple rightmost or leftmost derivations for a sentence, then this is called an ambiguous grammar. So this could produce multiple derivations and multiple parse trees. So essentially what that would mean is that one sentence in the language can have multiple meanings, which is of course not what you want as a programmer. You want to write a program that has one defined meaning, and if, depending on whatever derivations you take through your grammar, you can get a different parse tree, then of course your compiler does something wrong. So you need to be sure that your grammar is ambiguity free. Now, at first that doesn't sound so complicated, but let's look at a typical example, which is already quite a couple of decades old. And this is an example when you try to write if-then-else statements. So if you use more than one if-then-else statement, so you want to nest if-then-else statements like this here: if expression 1, then, if expression 2, then assignment 1, else assignment 2, then the question that shows up is, which of the if statements is this else belonging to? So is this else belonging to the first if statement, to the inner if statement, to the second one here? So which would mean if expression 1 is true and expression 2 is false, we use that one here. Or does it belong to the first if statement? So if expression 1 is false, we use that one here. This obviously has a different meaning. So if you tried to express this in a grammar, You could write it like this. So you start with a non-terminal symbol statement, and from statement you can either derive a sequence non-terminal symbol if, so this is just a keyword of a language, then a terminal symbol, non-terminal symbol expression, another terminal symbol then, another keyword, another non-terminal symbol statement, terminal symbol else, and non-terminal symbol statement. Or you could just derive if then without an else, or an assignment, or of course, if you want to write a more complete language, any other sort of statements. So if you take rightmost derivations, you can now have two different rightmost derivations depending on if you choose rule 1 or rule 2 first. So this actually decides on if the else is matched to our first outer if. This would be if you would derive rule 1 first here. That one here. Or if you use rule 2 first to match it, then you had if then, and then you'd match the rest, the inner if, with its else using rule 1, which might end up in this derivation here. So this is a real problem, and this problem has concerned compiler writers for quite some time. So you need to be careful when writing grammars, because this is absolutely well to specify, but this creates grammars which doesn't make it easy to actually work with them. So what can we do to remove this ambiguity? We can try to modify the grammar to include a rule that determines which if controls an else. So we split up our rules here and say a statement now is if expression, then just a simple statement, or if expression, then another rule with else statement, or a simple assignment. And this with else tells us that it can be derived to if expression, then with else, another with else, or an assignment. So this solution restricts the set of statements that can occur in the then part of an if-then-else statement. This accepts the same set of sentences as the original grammar. If you don't believe this, try it out. But it ensures that each else has an unambiguous match to one specific if. Still, the programmer has to know which rule applies here in order not to make any errors. So essentially this makes our grammar easier, but our programming language isn't getting any better maybe. So let's look at an example here. So our modified grammar, which we just repeated here, has only one rightmost derivation for the example. So again, we have our example here, if expression 1, then if expression 2, then assignment 1, else assignment 2. So we start with a statement, and now first we match this rule here, if expression then statement, and then we expand this statement here again to expression then, if then expression then with else statement. We can then replace the last one with assignment, and then we finally can replace that assignment here and are finished. I encourage you to try it out to see if you can get any other derivation from this, but you'll probably find out, no, that's just one possible rightmost derivation, because otherwise you'll find that there will be some conflict and you cannot derive this expression, this example expression, using our grammar. So our notation we've used here is a bit of a more modern abbreviated annotation. The traditional notation to represent context-free grammars is called the Backus-Naur form, or just BNF. So BNF denotes non-terminal symbols by wrapping them in angle brackets. So our sheep noise would be written like this one here, and terminal symbols are underlined here. And the symbol : equals means derives, and the symbol pipe character means also derives, so an or. So in BNF, our sheep noise grammar becomes this one here, where we must notice that there's an underline missing for the bar characters in our slides here. So just imagine there would be an underline. So if you see some papers or some grammars specifying it using this, you know, this is the Backus-Naur form that was introduced, but this is just another way of writing grammars, which is absolutely equivalent to the way we use in our slides here. And why was it used in that way? Well, because it was simply easier to typeset, because back in the 1950s, when Backus and Nauer invented this representation, you had no italics characters, you couldn't print in bold characters, you didn't have an arrow character. So essentially that was easier to print on a 1950s mainframe printer, which was quite restricted. So we've only looked at context-free languages so far, but there are other languages, and one of the persons who has worked on this is actually not a computer scientist, but a linguist, philosopher, cognitive scientist, historian, social critic, and political activist. And you may have read some stuff written by him already. This is Noam Chomsky, born in 1928, and he was concerned, well, as a linguist, with first, human, natural languages. But still, he generated results very, very relevant, because he tried a formal approach to specify not natural languages, and his approach actually determined classes of languages or classes of formal grammars, and this is called the Chomsky hierarchy. So in this hierarchy he defines 4 types, 0 to 3, of languages, and these types have increasing complexity, and we start with regular languages, and this goes to languages we call recursively enumerable. So we start with regular languages, and you should know them. These are the languages that can be detected by a regular expression or a DFA. Then the next more complex type of language are context-free languages, which we've seen before. Then we can also have context-sensitive languages and recursively enumerable languages. We'll take a look at some examples for the other types later on in this course. So accordingly, as we've also seen with regular and context-free languages, each language of a type that has a lower number requires a more complex method to recognize. So regular languages are very simple with DFAs. Context-free languages already require you to define recursion here inside of your grammar. And then we have context-sensitive languages and so on, which require even more overhead to actually specify them correctly. So we've learned a bit about parsing. We'll go into more details about how to construct parsers, how to write grammars for those in the upcoming lectures. So here are some very old references. So compilers, as we've seen, are an old research topic. So the Backus and Nauer paper here was written in 1963, revised report on the algorithmic language Algol 60. So they actually invented this EBNF notation or BNF notation to design a back then new programming language Algol, which is the ancestor of so many languages like Pascal or Modular, which were very popular in the 1980s and 90s. And Chomsky has a paper already also written in 1963, and this is a paper on the algebraic theory of context-free languages. So these are pretty formal, this Chomsky paper, but if you're interested, of course, I encourage you to take a closer look. So that's all for today. Thanks for listening. Until next time.